Hi everyone. We're just going to wait a few more minutes for everyone to get on the platform and then we'll start with the session. So we're just going to wait a few more minutes.
Danny, I've got to mention, can you share your screen? Thanks.
Okay, so we've got a good number of attendees now in, so good morning, good afternoon to everyone. My name is Stacey Roberts and I'm the IPLS Professional Development Manager. So thank you for attending this session on IPLS computing. Just a few housekeeping rules before we start. So there is a questions and a chat box available to you. If you have any questions throughout the session, please do pop them in there and we will answer them at the end for you. I have with me this morning Danny Nichols, who's our presenter for IPLS computing. He also created the original professional development module for us, so is an expert on this field. So if you have any questions around computing, Danny will answer those. I will answer anything on IPLS and the organisation, so please do fire them away to me, and Christian is also on hand to help with anything technical. Just to let you all know, this session is being recorded and will be made available to you all via YouTube and a space on our International Schools blog. So on to Danny and the session. So thank you very much.
Okay, thank you, Stacey. Good morning, good afternoon, everybody. Thank you for joining us. I'm trying something new with this session in that PowerPoint does subtitles automatically now. I'm going to try it out and see whether it works well or not. If it's rubbish and it starts putting out gibberish, then I'll stop. But it seems to understand me, which is a good thing. So I tend to talk too fast. I'll do my best. So thank you for joining us for the presentation. I'm going to just jump forward. He says, hopefully. And just a very quick introduction onto the IPLLS. And again, Stacey can answer some of these questions later on for you as well if you've got anything. But IPLS is the international primary and lower secondary curriculum. I'm going to focus mainly on the primary side of things today, but obviously the curriculum content goes up to lower secondary as well. It's a complete toolkit for you. There's lots of resources and the PD support and so on, some of which we're going to dip into today. So if you want more information about the IPLS proper, we'll talk to Stacey later, and please put questions in the chat box and we'll answer those as we go through. So an introduction about me first. My name's Danny. I'm Oh, one of the things I do is I deliver teacher training to student teachers, to initial teachers who are in their first year before they go into schools. So I do the computing lectures for those students, and I teach them how to teach computing as well as science as well. And I go into schools and deliver training for them. If you want to get in touch with me after today, my details are up on this slide here, and they'll be at the end of the presentation as well. I have a blog, there's a Whiteboard blog, and you can tweet me at Danny Nick, and there's my email address as well, or contact me via Stacey, fire your questions to Stacey, and she'll pass them on to me as well. So any questions, please, through the session, please throw into the chat box down there on the side there. So there's a couple of sort of aims that I'd like to get through in this session. We've only got 45 minutes, so we'll see how much this we can get through. We want to look at what is computing and what is computational thinking, which is a sort of the underpinning bit of teaching. We'll look at some of the terminology. I know a lot of questions about some of the words that are part of computing that are very particular to the computing curriculum. And we'll spend some time thinking about some examples of offline computing as well as online computing, because there's quite a few things you can do to teach the principles of computing without actually having to be on a computer. I know sometimes tech is a little bit unreliable. It's not always available in a lesson. You may not always have a whole suite of computers. So there's things we can do which let you teach computing, but you don't actually have to have a computer physically present in the room, apart from maybe what you're presenting on as a teacher, which kind of helps. As Stacey's already said, we'll make this presentation available to you at the end. We'll put it online so you can download it. I have produced a little pack of handouts, which I normally do as part of sort of the longer training session. We'll make those available as well. There'll be some links in there, and there's some links in the presentation, and there's some ideas and bits and pieces in the files. So we'll make those files available to you. So although I'm going to sort of fire a load of stuff at you, you'll then be able to go through these links at your leisure and take some of these bits further. A lot of what I'm going to try and do today is point you towards other places where you can get some help, because there's a lot of good stuff out there that's supporting computing and coding. Okay, so a little introduction. First, I mean, we are in an increasingly technological world. There are computers all around us all the time, and things that maybe we don't think of as computers are still computers. So in the last 24 hours, you will have used a whole different array of computers, maybe less so because we're still a little locked down, but in an average day where you may have been back in the day when we were allowed out of the house, train tickets, you may have gone to vending machines, you may be on cash machines. If you're out in your car, there are computers in your car. So for the children, they're in an increasingly technological world, and all of these things involve computers. And so with the children and ourselves, you can spend some time just trying to think about how many computers have you kind of come into contact with just in the last 24 hours, maybe even this morning already. You'd have checked the emails on your phone, you might have looked on your iPad, you might have, obviously you're on the computer now listening to this. If you watch something on Netflix or on Amazon Prime and you've plugged your Fire Stick in or something, we're using computers. So we have a very technological world of things that we can use all the time. So we have this computerized world. It's not going to get any less computery. We need to be aware of what we can do to interact with this world. And also the children of now are going to be hopefully creating things that run on these computers. They might be designing things, designing apps, working in computers and creating things for the computer. So the computing curriculum that came in a few years ago when they sort of revamped the curriculum and we lost ICT and became computing, there's three main strands to the curriculum. There's computer science, which is basically looking at algorithms and coding and computer networks. Then there's information technology, which sometimes gets overlooked now. It was in the past the main component. It was designing and creating digital content. So it would be creating things in PowerPoint, it would be creating things in Publisher and Paint, it might be using the internet effectively to do searching. But creating digital content is still there. doesn't always have to be Microsoft apps. It can be now creating things on an iPad. It can be making your own podcasts and so on. That's the sort of strand in there. And also there's a digital literacy strand. So it's staying safe online. So your online safety. It will be evaluating digital content. Pretty big these days in an era of fake news, where Twitter and Facebook are trying to flag the fake news that's out there and being posted, and social media is contributing to that. But also saving files and backing files up and all this kind of thing, just to keep yourself safe and organized online. So they're the three main strands. And if I sort of click to this screen, this is taken from the primary national curriculum for the UK. I've sort of pulled the words out into different boxes based on the columns. So the top row is your computer science row. So Key Stage 1, again, the word algorithms is in there, creating and debug simple programs. And then Key Stage 2, design and write debug programs, repetition, use logical reasoning. One thing I normally do with my student teachers when we first sort of approach this is to actually just look at the curriculum and take a pen and just underline the words you don't know, because there's lots of words, there's a lot of terminology in the curriculum now. We'll go through some of these words in a minute. In the handout, I normally have an activity where we chop and change, we chop up all the words and the definitions. We kind of get to match the word to what they mean, but we won't be able to do that so much today. But yeah, if you're looking through this, take a look at the curriculum and we'll go through some of these terminology, these terms and phrases in a minute. So the IT strand, use technology purposely to create, organize, store content. So that's just making things using software. So it might be, say, Paint, Publisher. You may have bought into bits of software like Purple Mash. You may just want to use simple programs on your computer. It might be iPad creation things like the iPad Paint programs and so on. And then Key Stage 2, searching. So using searching effectively to find your files, and create and combine a variety of software. So that's, again, digital creation. There's lots of scope for digital creation, and that can be very much cross-curricular. It doesn't have to be in a computing lesson. That could be things that are done within science, within English, within geography. And so you're using this technology in other lessons, but it's contributing to the computing curriculum. Then the third strand is the digital literacy, and digital literacy is common uses of information technology beyond school. So that's kind of what we just did with that previous slide on computers around us, and think about where all these things are. Use technology safely and respectfully, keeping information private, not sharing passwords, not sharing personal details online, and so on. And then taking that slightly further, evaluating digital content, to be discerning and evaluating digital content over here. The kind of judging where the websites are coming from and whether you can trust the things you read online. Just because it's on the internet doesn't make it true. And we're all falling foul of that these days, and just taking the first thing we see on a Google search and believing that. And children need to be taught, and grown-ups need to be taught how to judge that content. And again, there's aspects within the course where we can look at that. And again, safely, respectfully, recognize acceptable behavior, and so on. So that's kind of the national curriculum there for computing. So my thing's telling me I've got a slow connection. I'm hoping I can still be heard okay. If there's problems, somebody ping me in the chat there. I'm hoping everything's good. So let's try and go through some of this terminology that we've got here. The big one that I think a lot of people get very confused and concerned about is algorithm. So an algorithm sounds quite scary, but really all it is a set of rules. It doesn't even have to be on the computer. It can be a step-by-step set of instructions. So if I wanted to give you instructions on how to get from my house to the local supermarket, and I gave you a set of instructions, that's basically an algorithm. And so you can do simple algorithms in the classroom that don't go on a computer. We're just programming ourselves. We're giving it in words instructions. So bug is just an error or a mistake, and then the process of debugging, which again some people get quite concerned about, is just looking for the mistakes and fixing them. So if I've told you to turn left instead of right, I go back and look at my program, I look at the instructions I gave you, and I make a correction. That's debugging. Data, structured set of numbers, so that's kind of things often you might deal with in a spreadsheet, but also it could be text, it could be sound data, it could be images data, and so on. Anything that's processed by a computer is data. Input is the things coming in, so provided by maybe keyboard, or maybe by mouse, maybe a touch screen, or by an interactive pen sometimes now with these flash new iPads and Windows machines where you can use a pen as well. So that's the input, that stuff coming into the computer, and then the boundary between the computer and you is often called the interface, often how we interact with the computer. The output is whatever the computer puts out. So that would be maybe pictures, it might be video, it might be audio via a speaker, it might make something move, so it might be you're programming a floor roamer and you push the buttons and the output is the way that it moves across the floor. And then a couple of sort of codey ones again. Pixel, the pixel is the posh term for the dot on a computer screen. So your computer screen is made up of thousands and thousands of pixels, and the number of pixels you have defines the resolution of your computer image, and so one individual dot, which can be kind of any color, you can change that color of the pixel. They're the pixels, and that's what makes up your JPEG on the screen, or your picture on the screen, or the image you're watching now is made up of pixels. A program is a set of instructions, so an algorithm is maybe one part of a bigger program. So one algorithm might make up a wider program with lots of different algorithms within that, which make up a bigger program. One that a lot of people don't always know is an old word really for what you create on the screen, a graphics object. So a character in a game or anything that moves around on the screen is called a sprite, which is kind of a cool little word. And then a variable is an interesting one. That's kind of how computers keep data inside them. So it might be something that changes. So it might be a name, it might be a game score, it might be a particular set of numbers. So you enter something into the computer remembers it for a bit and does something with it, and we call that a variable. That's quite important when we get into Scratch and we start looking at maybe making a game. And so you want a variable to be the score, and every time you do something, the score goes up by 1 or by 10 or by 50, depending on what you've done. So variables are quite important when you get into Scratch programming. So again, early on, Key Stage 1, you wouldn't be going into Scratch, but as you get into sort of Key Stage 2, you definitely should be looking at Scratch. And so that's something I'll flag up later on. So those are some of the words. And again, any other questions people have got, please throw them in the chat. There are lots of websites and lots of sort of handouts and stuff you can get online. I'll give you some links in a minute where they have posters which you can put on your classroom wall. You can cut them out and make a nice display of some of these words, because obviously getting the terminology right is quite important, and getting the children to think about themselves as coders and the computational thinking. I'll put this link again out later on. You get it through the presentation. Quick Start Computing. This comes from an organisation called Computing at School, who are producing some excellent resources for the teaching of computing in the UK, but also internationally. So if you want a comprehensive PDF file with lots of information and lots of ideas and lots of support, this is the #1 thing to kind of start with. So the link is there. If you Google Computing at School, Quick Start Computing Guide, you'll find it. It'll be the top hit you get on Google, and it's brilliant. There's lots of good stuff in there that can help you as a starting computing teacher, if that's what you are, to build up your skills and get some ideas of things that you can do. The Computing at School website is definitely worth bookmarking and remembering for later on. The underpinning thing for a lot of the changes that came into the curriculum is computational thinking. And again, it sounds scary. If you break it down, it's not as bad as it kind of sounds at the beginning. So computational thinking is getting the children to start really thinking logically. You take a program, understand the problem, and develop some solutions. And we do that all the time through school and in our working life as well. We don't think of it as computational thinking. The difference is that when you present your solutions, it could be again, offline. It could be something that's a human can understand, or you might present these solutions in a way for a computer to understand. So it might be you're writing a program to solve that problem, or you're writing an algorithm to solve that problem. But it doesn't have to be. The computational thinking is a way of thinking that is just logical thinking. But obviously, it leads into creating code and making computers do things that maybe solve particular problems, and that's where it links into this curriculum quite well. So it's looking at the problem the way which maybe you can get computers to help us to solve it. So the first thing you need to do is think about the steps you need to solve that problem. Then you would get your technical skills to get the computer working on the problem, and then come up with some kind of solution. It might be a simple thing. It might just be working out the area of something, or looking at a sequence of numbers. But it might be more complicated than writing a full-on computer game to simulate a rocket flying to the moon. There's lots of ways you can take this. Depends on your children, depends on the age you're teaching. There are 4 kind of strands to computational thinking, and if you go through the guide I just gave you, there's examples of all of these, and we'll go through a few of these now just to sort of give you some basic ideas of where you might start with this. The bottom right, I'll start there. Algorithms we've talked about before, that's creating some code, but also there's abstraction, there's decomposition, and there's pattern recognition. I'll go through what those things mean on the next couple of slides. So don't panic if that slide looks kind of meaningless. The algorithms we've talked about before, that's making steps and making rules. So that's writing simple sets of instructions. Pattern seeking might be looking at the similarities with problems. Have we met this problem before, or can we come up with a simple pattern which would help you to solve this thing? So it might, as I say, it might be working out the area of a particular shape. It might be looking at a number sequence. It might be making a function machine. If I enter X, it spits out Y. There's ways you might do that, very much linking it to maths, but also possibly science and elsewhere. Decomposition, again, sounds scary. It's breaking a complex process down into its simpler parts. So what you're looking for is taking something that overall looks quite complicated, and then sorting out smaller steps which can take that whole process and make it simpler to do. And again, I'll give you some examples of that in a minute. And also abstraction. You may have a whole problem you want to solve. How much of that problem, how much of the things that are in there are actually not necessary to worry about? Can you get down to just the bare bones, and that's all you need to fix? Again, I'll show you some stuff in a minute that will help you with that. Some more links, again, for computational thinking. When you get the presentation, click on these for some extra reading. There's a lovely set on BBC Bitesize. Google for Education have a little mini site about computational thinking. There's a nice article from Miles Berry, who's written a lot of the resources for computing at school. His website's well worth a look. And also there's Scratch have a guide to computational thinking. So those links are there for you to go off to if you're interested in this, and I'll give you more links later for other things. So let's start with patterns. Patterns would be trying to find patterns in the things you're looking at. Can you make a rule? And if you can make a rule, then it's easy to write a program to spit out an answer. So I've got some math examples. It might be you can use Excel quite easily to make something called a function machine. And so I've got actually a little picture I've got up here. You might enter 2 numbers into 2 boxes, and the function machine spits out an answer. And that answer is take the 2 numbers and do something to them to get that answer. So it might be take 6, double it, and add the bottom number, or whatever. So you've got a function, and then you can either create a function machine after children to work out what they think the function is, or they can create something themselves. We're not doing any complicated programming. We're just using an Excel spreadsheet and a simple Excel formula. It might be calculating number sequences. You might give them 4 or 5 numbers, and each time you times the number by 3 and add 2, or double it and add 2. And so once you've given them 3 numbers, can they see if they can work out what the sequence is? Could they then generate an Excel formula to put into the next 3 cells to continue that sequence on? So it's just looking at, equals C3 times 3 plus 2, those kind of things where they can work out what the function is. It might be giving out commands to draw particular shapes. So if we're looking at maybe linking this to maths, we could do a human robot, which I'll talk about a bit later. I'm going to be the robot, and the children have to give me instructions to draw a particular shape by walking a shape on the floor or give instructions to each other. So could you get them to draw with them walking? Could they walk in a square, or could they walk in a triangle? Could they walk in a pentagon? So yeah, move forward one pace, turn 90 degrees, move forward one pace, turn 90 degrees, and so on. And then could you simplify that down? Well, we're doing a lot of walking forward, turning 90 degrees. So to be a square, you need to say, right, do 4 lots of walk forwards, turn 90 degrees. And go from there. So we can use repeating, and again, Barefoot Computing has some nice links here, other ideas you can do for teaching patterns. So if you're interested, if you want to sort of take that further, do please look at that. Decomposition is taking a big problem and breaking it into smaller parts. Again, this doesn't have to be a coding example. This can be things like, I want them to plan a trip to the zoo. I want them to plan a school fair or a science project, or plan an event. So you take that overall event, which is we're going to the zoo, but we need to break that down into the smaller parts. We need to sort out the booking, we need to sort out getting the tickets, we need to sort out the bus, we need to sort out the food, we sort out keeping the parents informed, and so on. So how do we do this? We break it down, and maybe individual children would work on different bits of that as a whole project. We could look at taking a computer and breaking it down. There's some nice websites which do this. So things like iFixit do computer teardowns. If you have a nice old computer lying around, there's often a few in the back of the technician's room at school. Maybe you could take that computer, and we can take the computer apart and look at the bits that make that computer work. So you might find the sound card, the motherboard, the CD drive, the hard drive, the speakers, the mouse, the keyboard. What do all those bits do? We're taking a bigger computer and looking at the smaller bits of it. If you're allowed to take gadgets apart, if you've got an old gadget and you're allowed to get in, because some of these things are so locked down and hard to open, you could take a look at that as well. And things that would help with this, again, we're all still sort of kind of locked down, not all in the classroom now, that you could do these collaborative projects online. So think about using things like Google Docs, where you can all work on the same document or the same presentation, the same Word file, to all type, but all be in different places and work asynchronously. Or you could use something like Padlet, if you've not seen Padlet, where you get an online space where you can all post ideas. Again, you just got to share the link around. Anybody with that link can add ideas to that page, and they're really good for collaborative projects online. If you're not in the classroom and everybody's spread out, you can still do this kind of thing. But even in the classroom, you can set it as a homework activity, or each table has a computer and they can share ideas. Another good website, if you're interested, is something called Apps for Good, who have lots of resources on designing apps. So children can make their own apps, and there's some guides and things to follow through. And again, you might use that as part of a decomposition project. We're going to write an app, so let's break it down and work on different bits of the app and then combine it back up. So Apps for Good is well worth a look as well. Abstraction is kind of really just making things simpler. If you're designing a game where you've got an aeroplane flying around, do you want to spend loads of time working out how you simulate gravity, how you simulate lift, or is it just a case of, I'm going to make this flight go up and down and left and right, and let's not worry about the fact it's not a true Microsoft flight simulator that takes years to develop. I want to make a little thing fly around the screen. So we simplify it. We forget about gravity. We forget about friction. We just make it simpler. A good example to show with the children is a transport map, a tube map. So I've got the London tube map on the screen there, and there are websites out there which have a kind of what it really looks like. I mean, the London map was one of the first, or was the first, to take a transport system and show it in that kind of simplified, dead straight lines and 45-degree angles and so on. It's not exactly how it looks, but it's brilliant for navigating around the metro system, the tube system. It's really good. On the other side of the screen, there's what it really looks like. It's all over the place. That's much harder to work out where you're. That shows exactly where you are in London, but you don't need to know that. I want to go down and grab a train and get to X, Y, and Z. You don't need the extra information. I just need to know how the stations link. The distances are slightly irrelevant, so you can take that. So abstraction might be things like they might have watched a television show. Could you summarize that show for me in a storyboard of 6 frames or 9 frames? So 9 boxes on a Word document, print it off, and they can just draw what happened or write the key points. I don't need every scene, I don't need all the detail or all the dialogue, I just need just enough detail to get the plot across. So it's just a summary thing, it's a summarizing activity. Could they make a kind of transport map for the school, how all the classrooms link up, or the town centre, if you want to show how to get to the town centre, or show how the town centre is all linked up? Could they make a transport map, just simplify it, just where the things are, but not exactly positional, but just where they are? How do you get around the school? You could also do network models. There's some things, I've got a guide for a slightly involved class model when we're all back in class, of how you would model the internet and sending an email to somebody, where you write things on bits of paper and you number it in a certain way and it goes to particular tables, and one table acts as the job of the router and the mail server sending information to different tables. It's a bit complicated to kind of explain in the time we've got. The handout is a kind of guide to how to do this. It's worth looking at when you get it, and if you have a chance with a class down the line, it's a nice way to model it. And there are other models out there for modeling and looking at network models. Again, the wires aren't exactly how they should be. It's kind of a simplified thing, and there are links on Barefoot again if you want to look at that. Again, if you have any questions about any of this, please fire them in the chat, and we'll deal with those later on. I'm trying to keep an eye on it. I'm not sure if I can see any questions, but that might just be my view. So computational thinking, ways you might approach with it. Things they suggested on the Barefoot site. Sometimes it's just tinkering, playing with things, do some experiments, play with the software, play with the devices, get a feel for how it works before you go and write something properly. There's creating, so taking something and actually designing it, using something like Scratch, or using something like Logo to create a thing and design a thing, and what apps for good will show you how to do that as well. Debugging, so things aren't going to work fine, there's going to be problems. You use your skills to break it down, think logically, look at where the errors might be, and you find and fix them, and that's going to be part of all the things we do. The debugging skills are in there. Collaboration, working together. This thing is not just the thing that children should be doing on their own, although they can. It's always better if we can collaborate, and so several students working together to create a thing is better, because you get these collaboration skills, different people working on different bits and bringing it together. And then persevering, just keep it going. Again, it's skills that we should be teaching the children, that if at first you don't succeed, have another go, try again. Your program may not work first time. Some of these things are hard. Learning Scratch is hard. It's like learning another language sometimes. So you've got to persevere, and you've got to try. And try again, not just give up. And we try and teach those skills to the children, I'm sure, in a lot of things we do. They've reappeared, let's ignore that. So algorithms, it's not always possible, as I said, to do coding on a computer. There's a really cool website called CS Unplugged, which has the link there. And on CS Unplugged, you can have a whole world of different ideas of things you can do online. I've picked a couple to kind of go through with you now. One of the things we do is just simple things like drawing a monster. So I've got a monster in my head that I've drawn. I have it hidden, and I give the instructions to the children. So right, follow these instructions. So draw a circle, add 2 eyes, add 2 horns, add 6 legs, add a pair of wings, and see what you've got. And it's up to them to go and draw that and see, and then we can compare with each other. And you should get lots of different monsters, all kind of following those rules. We're never quite looking the same, because I maybe wasn't clear enough in my instructions. Are there things I'd need to change to make it more specific? The children could then go away and do the same kind of thing. One might draw a monster, keep it hidden, and they've got to write an algorithm to tell their partner how to draw it. I've seen similar kinds of thing with Lego. If you've got 2 identical piles of Lego bricks, and child A makes a little shape with their Lego, they've got to give instructions to the other child who can't see what they've made to build the same thing. So again, you've got to think about how specific your instructions are, how clear your guides are. Are you telling me exactly where to put it? thinking about positions, thinking about shape and color and size. You make sure you get the right blocks. There's some interesting descriptive skills there you can do. It's valid computational thinking. It's nowhere near a computer, but it's just fun things to do where you're getting them to think about giving instructions to somebody else. Human robot, you may well have seen the B-bots. These are little programmable floor turtles. There are other kinds of turtle out there as well. The B-bot is one that is very common in UK schools, definitely, where you program in a sequence on the buttons and then send it off, and it follows your commands. So go forward, turn right, go forwards, turn left, go forwards, and so on. But you could use a person as a robot rather than messing around with B-bots. So children could instruct each other. So you might have a group of 3 or 4, and one is the robot, and they work out their commands to get the child from one part of the classroom to another, picking up a device or picking up an object and delivering it somewhere else in the classroom, putting it down in the box. They might write down the sequence first and then read it out to the robot. You can also quite easily print off little cards, and there's websites out that give you these done already, cards with arrows and turns and instructions on, and you can lay these down on the table to build up your sequence first, and then let your human robot wander off and follow that sequence. And again, if they go wrong, they've turned left instead of right, they haven't quite gone far enough, you debug your program, pull them back to the start, and try again. So it's coding, principles of coding without actually using a device. You would then possibly, you would then obviously move on to using a floor turtle or a Roma for real as a next step. But as an introduction, as an introductory lesson or the start of a lesson, start with that. I like the fact that the subtitles come up with aroma for okay, sorry. Writing code. Again, if you're introducing the idea of making a program, which you might then end up using Scratch or later on maybe things like Python and so on, you've got to start with thinking about how the program works in a kind of everyday language, so you get the idea. So you're pretending you're coding, but you're not really coding, you're just going through the process of. So it might be that you this is a game for testing math skills. I'm not running it in Scratch, but I'm just saying, like, what I want to do is I'm going to do 10 times of ask a math question with 2 random numbers. It's going to ask somebody for a number, they're going to enter the answer. If it's right, say correct. If it's wrong, say wrong. And so that is something that's my structure that I would then try and build that using my program. So I've got an idea of what I want it to do, how I'm going to do that in Scratch. You might start to think about drawing shapes. So again, I want to draw a triangle. What do I need to do? So the first thing is, again, I'm going to move forwards a centimeter or 100 units on the screen. I'm going to turn through an angle, and I'm going to move forward again, turn through an angle, move forward again. So the question first of all to the children is, well, what is the angle you're going to turn through? It's not 90 degrees. What angle do you turn through? And then how many times do you repeat that? So if we're drawing a pentagon, you move forward 100, turn through a 72 degrees, move forwards, turn through 70 degrees, move forwards 100, and so on. Or you could just say, right, 5 lots of, move forwards 100, turn through 72 degrees. And one of the things that, again, is working in some cross-curricular skills is looking at those angles. And there's actually a formula to the angle. A pentagon, you turn through 72, a hexagon, you turn through 60, and so on. And so the children could work out the program, the formula, which is basically, it's 360 divided by the number of sides gives you the angle you turn through. So it's 360 divided by 5 gives you 72, 360 divided by 60 gives you 60 degrees, and so on. So you're doing a simple pattern seeking, and then we're looking at, well, how do you draw a nonagon or an octagon or a decagon and so on, and they can work out the angles they need to change. So how many times do you repeat it? What's the angle you turn through? We can draw shapes. So this is actually then using Scratch to do that. I've hidden under the box is just the pseudocode, but it's draw the pentagon and then turn through 60 degrees and draw it again, and so on. There you go. So repeat 5 times all of this. So the first thing is drawing one side of the pentagon. We're repeating the pentagon, we're repeating the line 5 times to draw a pentagon, then we're repeating the whole thing 5 times to draw the flower. and you could change that to repeat it 100 times and turn through 7 degrees or whatever. And if you do 100 times, 10 to 36 degrees, and so 3.6 degrees, sorry. And so you can make a very, very sort of stylized repeating pattern. If any of you remember playing with a spirograph toy back in the day, where you've got those repeating sort of circles going round and round and round and round and round, it's that kind of thing. So here's some, again, it's making it look a bit like Scratch. This is using Scratch blocks, but it's getting the children to think about how you might write a simple program in the Scratch blocks. Again, if you've not played with Scratch, this is sort of your next step of where to go. But it's thinking of set a variable to 0, and so the variable is going to be the thing you're going to say out loud, and you're going to keep doing this until the variable equals 9, and each time the variable goes up by 1, you wait a second and you say it out loud. So this is a simple program for counting to 9, basically. So you start at 0 and you go right 1, 2, 3, 4, and so on. So it's not a complicated program, it's just a simple thing for doing that. And this is a silly one, which is basically for the song, if you're happy and you know it, clap your hands, but put in Scratch format. So if emotion is happy and your brain knows it, then clap your hands. And then if you're happy and you know it and your body wants to show it, then clap your hands. So it's taking something that maybe the children are familiar with and turning it into a Scratch language. Absolutely no time to go through all the coding side of things, because that's a webinar in itself, and that's a day in itself, a couple of days in itself. But there's some really nice self-paced stuff which you can go through. So the Raspberry Pi website linked to Code Club have some gorgeous Scratch projects. You can print them off or just split your screen and have the project running down one side of the screen, and then Scratch open on the other side of the screen, and you can sort of follow through the projects that way. Scratch itself, if you go to scratch.mit.edu/ideas, there's lots of built-in Scratch tutorials. So you can have Scratch up with ideas at the bottom, which take you through things that you can do. All self-paced, and so the children that could be put in, given links, and they can work through this themselves. Again, if you're not in a classroom right now and children are working remotely, then maybe give them a Scratch project to work through themselves, and they can then share the link with you. You can see, once you've made a program in Scratch, you can send the link to other people so they can see what you've done. So you can actually take a look at it and they can share their games with each other. And also Scratch has these, it's a 200-page PDF file, because they're double-sided, but they're called Scratch cards, and each one, when you've printed it double-sided, each one has an idea on the front and then how to do it on the back, and they're color-coded and themed to different kinds of projects. So you can give a batch of these to children and just start working through. So it might be animate a letter, or a set of them related to playing music or making a game or doing some animation or doing something with a character. And again, if you want to yourself learn Scratch, they're a great place to start. If you want to start directing these to the children, they're a great place to start, and they can work through these at their own pace, or have them spread out. When we're back in classrooms, have these spread out on the tables and we pass these around so they can work on them and mix and match and share them around. If you want to take this further, there are lots of ways you can go in terms of things like the Hour of Code website. The links for all these will be in the handout, or just Google these, you'll find them quite easily. So Hour of Code has lots of nice on-screen web-based games that involve coding. So you can code Anna and Elsa from Frozen, you can code Ray and BB-8 from Star Wars, you can make them do shapes and you can make them do certain things. EduBlocks is kind of a simplified version of Scratch that covers lots of things, and the Code for Life website, where you can code delivery trucks using programming language. If you have iPads in your classroom or iPad apps that you want to use, Scratch Junior is brilliant for early years and Key Stage 1 to get an introduction to Scratch after they've played with Bebots. Maybe there is actually a Bebot app which you can play with, and something called Daisy the Dinosaur, again, which is a nice simple introduction to putting some code in and making a character do something on the screen. You've also got your Bebots. There's lots of other roamers that are out there, and the Bet show recently, there's lots of different companies making roamers that you program and they run around on the floor. Lego We Do, if you want to take this further, is programmable Lego, which you can code on an iPad or your computer and make the Lego blocks do stuff. Sphero is a little ball which you can program from an iPad, and you can make the ball roll around on the floor. It's a bit more it's a lot faster than Bbots. It's a bit more fun sometimes. It can change color and things like that. And again, for key stage, upper key stage 2 into key stage 3, the BBC microbits, which are cheap, bare bones cards, which you can plug into a computer and program and then make them do things. They're all good things. So as an extension, these might be things that you bring the children in to play with. The links are here for some of the things I've talked about already. I'm going to wrap up in a second and take questions. So just going through this quickly. Code.org and Hour of Code, Barefoot Computing and Computing at School are definitely good starting points. And then the Computational Thinking from Google and the CSM plug. The links for these will again be in the handouts, but they're there on the screen for you. And another website, this is the chap who does training in the UK. He, if you Google make your jam sandwich robot, you'll find him, because he has a video of him pretending to be a robot that makes sandwiches and the children give him instructions. It's called Phil Bag, and his website has lots of guides if you want to get some ideas on some of these things I've talked about. Again, his website's well worth a look. So I'm going to stop there in terms of the input, and we'll take questions. That's my contact details again, and that's Stacey's contact details as well. So if you want to get in touch with us after today, you can contact Stacey there. I'm sure she'll be happy to help you with aspects of the curriculum side of things in terms of getting involved, how you sign up and getting further training and so on. So I'll stop for a second and hand over to Stacey. I'm going to stop showing my screen, I think, for now. If I do that. Stacey, do you want to?
Yeah, thank you very much for that, Danny. That was extremely interesting, and I definitely learned a lot. So we've got a few questions in. The first one is a bit more kind of logistical. So the webinar is around where can I find the webinar once we've wrapped up today. So the webinar will be available on our International Schools blog and also on YouTube. There will be links to both of those for you, and we'll attach kind of the handouts in the International Schools blog. So you'll be able to find this webinar once we're finished with it. So, and then I've got a few questions for you, Danny.
Yep.
So the first one is, which is the best software to use for programming for Key Stage 1 and Key Stage 2?
Key Stage 1, you start with Bbots and floor turtles and sort of away from the programming. Actually sort of use a physical thing, I think, to get them the idea of an algorithm. And then probably something like Scratch Junior or Days of the Dinosaur, which are quite nice, simple things. If you've got iPads, they run lovely on there. And if you haven't got the iPads, then something like the Hour of Code, where you can make Anna and Elsa, so that the Hour of Code throws on the Hour of Code Star Wars, because they are very, very simple, and it takes you through step by step. So your first program is literally make her move forwards and then turn right. So if you want to introduce it to Key Stage 1, I think the Hour of Code website would be very good. For Key Stage 2, Scratch is really your best place to start. It's kind of, it's the daddy. It's been around for a long time, but it is very comprehensive, and so snapping the blocks into place to make your programs, definitely start with Scratch. And if you haven't played with Scratch, just Google Scratch. It's scratch.mit.edu. It's easy to find and it's free, so I would start there.
Cool, thank you. The next question relates to, how often do the students need to use computers or laptops during computing classes?
That's a good question. It doesn't need to be every lesson. As I said, you can do some of the unplugged stuff. So it may be that in a sequence of lessons, you may have a couple of lessons that are offline where you're teaching the computational thinking, and then a couple of lessons where they're carrying that further and using the computers. Quite often I've seen teachers will split the class maybe, and so half are using, because obviously having access to computers can be a problem. So you maybe split the class and half are doing something offline and half are using the laptops. It doesn't have to be every lesson. I think, again, there's the fear that we need to be on computers all the time. It doesn't have to be that way. It could be, yeah, a couple of lessons offline and a couple of lessons on the computer. They're going to need to use computers at some point as part of it, but it may not always have to be every lesson. And again, it might be things like Bbots and Romas and other devices that are carrying out the principles, but you're not actually on a laptop or an iPad. If that helps.
Yep, thank you. And then the next question is kind of two parts. So if you answer the first part, I'll then answer the second part.
Okay.
So is a textbook necessary for this subject?
No. I think a textbook itself, no. I think you can probably find enough stuff online, but obviously we've got resources on the IPLS that will help you. I don't know what in terms of what you provide, but a textbook, you can do a lot of it without a textbook. Probably you might need something as a teacher to help you, but I think a textbook may not be necessary. But you can find support. Obviously, we provide support for you as a teacher, and then handouts and so on that the students can use.
Yep. So the second part is, or are the resources in Active Learner enough for teachers? So Active Learn is where all of the curriculum documentation, all of the lesson plans, all of the further teaching support is available for you as teachers. It's broken down into year groups and into subjects as well. So there will be specific computing teacher guides, lesson plans, schemes of work, tests, assessments for you, all available on the Active Learn platform. So that's all there to support in your teaching.
Yeah. Yeah. So textbook no, but there should be enough support to help you to do that. Yeah, definitely.
Yeah. And then the next question, is there any way that computing can be integrated with contents of other subjects, so cross-curricular?
Yes, and a lot of ways I think that's the best way to teach it. You know, I like to think, do we have pen? You know, we don't have pen lessons. We have lessons that use pens in maths and science and so on. So the computing is really your tool. And there might be situations where you need a specific computing lesson to go through a particular aspect of how to use the program, how to use Scratch. But I think, you know, if you're looking at drawing shapes, then that's a maths lesson. If you're looking at function machines, that might be a science lesson. If you're looking at using Scratch to animate two characters talking, well, you write that in a literacy lesson, then they talk it. You know, so it should be that the Scratch, once children have got some of the basics that maybe will be taught in a computing lesson, a lot of these computing skills are well set up to pop up in a literacy lesson, in a math lesson, in a language lesson, in a geography lesson, in a history lesson, and they don't have to be just in computing. And I think the way you can teach, make sure you've got a lot of the computing, is to make sure those cross-curricular aspects are in there. Maths, definitely, science quite a bit as well, but a lot of other subjects, it'll pop up quite naturally in there. And the other aspects we've not really talked about so much, the digital content creation, the using Publisher and Excel and PowerPoint and digital cameras and making videos, they're going to crop up in lots of other lessons as well. You don't have to have a computing lesson, let's make a video. That could be, let's film the results of our science experiment. Let's make a film that explains about the Romans or the Vikings or whatever. There's loads of aspects of the computing that will just be in your subjects, hopefully. And as a computing specialist, you might need to track all that and show they're doing it, but it can be a thing that will be outside the computing classroom.
Cool, thank you. There's a few kind of curriculum-based questions, which I will try and get back to everyone on. So what I'm doing is I'm picking out ones that Danny can speak about and answer for you. So quick question, do these programs work on Android? Danny, do you know?
Some do. I would need to go and double check. Most of them normally now are both, not just on iPads. And a lot of them, especially the browser-based ones, will run on anything. So the Hour of Code stuff is browser-based. It's not using Flash. It's all HTML5. So if you've got Android tablets, they'll work. They should be fine. I need to double check on a few, but as far as I know now, there's normally an iPad version and an Android version. Definitely.
Yeah. Okay. Is there any way I can link Scratch programming with Visual Basic for Key Stage 3?
Ooh, I don't know the answer to that one. I know Scratch sort of links into sort of Python, and you can take it further. Something that might be worth looking at, not Visual Basic, I think, but the EduBlocks. He's created a sort of a thing that's not quite Scratch, but not quite. Let me try and find it. It's edublocks.org, and he still has. It looks a bit like Scratch, so it's like you're doing Scratch, but it then can switch easily into other things. It does Python Raspberry Pi low. Visual Basic, probably not. So I may have to pass on that. It's been a long time since I played with Visual Basic.
Someone's actually popped in the question, Scratch 2.0, no.
Yeah.
And then someone has asked, what is Scratch? Is it a programming language? Is it a programming language? If you could just give a quick, what is Scratch, please?
If I bail out my PowerPoint, because I've got Scratch open here, can you all see that okay? Have I sort of lost? Let me show screen again.
Yeah.
You can see my screen. Right. Yeah. Right. So this is basically Scratch, and what you've basically got with Scratch is it's kind of a programming language, but you don't have to program words. Everything comes from the blocks. So at the moment I've got a cat, and I've got this little program here that when I make him do my program, he repeats 5 lots of what I just talked about. So he's moving 100, turning 72, and he's doing it 5 times. So you're making a program, but what you're not doing is actually having to write lots and lots of lines. I'm back in the day, had a ZX Spectrum, you had to write like 10 do this, 20 do this, 30 do that, and it was all handwritten. You don't handwrite anything in Scratch. All you do is you drag your components down and snap them together. And so down here you've got how you make things move, how you make things look. So if I wanted the cat to say hello, I can just drag that down and he'll say hello. If I want him to meow, I can get him to play the sound. Oh no, done that one. Play sound meow. So there we go. So we're dragging these program blocks down to make my program. It's nice and simple, and can get more complicated if you want it to be, but you can keep it nice and simple and just write simple things. And the beauty of the Scratch thing, if you click on tutorials, then these are lots and lots of guides on how to make it work. So it's definitely worth it. It's completely free. So I definitely sort of go to the Scratch website, just click on create, and then click on tutorials and just try a few of them out, and you'll soon get a feel for it. And children, Key Stage 2 children will pick this up really fast, and I've seen some schools try it with Key Stage 1. I'd start with Scratch Junior first, but definitely Key Stage 2, they'll lap this up, and most of them will pick it up quite quickly. It's us that struggle a little bit to get our head around it.
Cool, thank you. I think we have time for maybe a few more, maybe two more questions. So I've got one here. For lower grades, how do we teach them clearly so that they can really understand instruction? So how to draw kind of 2D figures?
Yeah, I mean, it starts simple. It's drawing. I mean, for lower down, you'll basically want to start probably with a Bebot or some kind of floor turtle, which you're just making move around. You can print off or download sort of mats which have sort of squares on them, and maybe make a plan of a little town or a garden, or some of them have coins and stuff on. And it's just a case of, can you get the turtle to move to the 10pp? So can you get him to move around the lake and end up at the shop? And so it's just writing a simple program. So they're not trying to worry about shapes, and maybe they haven't studied the angles yet. That's too early for them. But it's move forward, turn right, move forward, turn left, go backward. It's simple stuff. But the floor robot, and obviously then before they're coding each other and then coding the Roma, start it simple, and then if they've done that, move on to something like Scratch Junior or Daisy the Dinosaur, where you're making the robot move forward, get bigger, do a dance. There's nice simple stuff they can do, and that leads them then into Scratch proper, maybe sort of year 3, year 4 and upwards.
Cool, thank you. And then final question, which I think is fairly relevant to the time that we're all living in. Will social distancing in schools have a big impact on this approach? So kind of teaching the computing, the group work, that kind of aspect.
Yeah, I think that's the golden question at the moment. I think it might impact on some of the Roma stuff, because obviously you're going to need to sort of disinfect the Romas in between use and so on. So that might be something that's going to be a little bit more tricky, but you could have a session where they're maybe doing that on their own. One's writing the program and transmitting the program, put it on the board, and they all lay the cards out, and only one is touching the turtle and playing with the turtle. Some of the other things I talked about, that's where you look at the online collaborative software. So something like Google Classroom or Google Drive, Microsoft Teams, these kind of things, where you can collaborate without being in the same space. So if you have still got children that are not in the classroom, they can still work on a collaborative project using a lot of these tools now, like I mean, if you've got Google for Education, that will have Google Meet in there. You'll have Google Docs, so you can sort of write on a PowerPoint, you can write on a Word document, you might use Padlet, so they can still collaborate without actually being in the same physical space. When we get back into the classroom and we're still slightly distant, you could still collaborate. It might feel a bit sad, but table A is talking to table B and working on the same document via Google rather than passing bits of paper between each other. It's actually, the technology may well help some of that.
Okay, so we've just hit the hour, so I think we'll leave it there. If there are lots of questions that have been unanswered, so I will try and get back to as many of them as possible. But just a quick kind of reminder that the webinar will be available via YouTube and on the International Schools blog, and we'll send links around to that. So I just want to thank everyone that attended and questions that were submitted, and also thank you to Danny for this educational and insightful webinar on computing.
Thank you all for coming. I hope you found that useful. Let's say any questions, there's Stacey's details and there's mine as well. Please get in touch if you've got any questions. Let's stop there.